All right, well, our topic tonight is a review of differential equations. So, just a reminder, a differential equation is an equation that involves x, y, and the derivative of y. And there are many different notations you can see for the derivative of y. Obviously, we have y prime, y double prime. We could use f prime, f double prime, or we could use dy dx or d squared y dx squared for the second derivative. So again, different ways to represent the derivatives. One of the topics we focused on was called direct variation. We called K the constant of proportionality. Okay, so again, this is all review, and we had to know that formula y equals kx, and it is read y is directly proportional to x. Okay, so when you see that phrase directly proportional, we need to know that's y equals k times x. If it was inversely proportional, it would be y equals k divided by x, but directly proportional is kind of linear, and maybe that's a good word to write down with it. You're just thinking linear. Y equals kx like y equals mx. All right, so how is that going to apply in maybe some of our problems? The learning rate, so example 1, the learning rate for skill S is proportional to the difference between the maximum potential learning that skill M and the amount of that skill already learned. Write an equation that describes this relationship. All right, so the first thing I want to pull out of there is that it said it is proportional to. So right off the bat, I'm thinking y equals kx. So something is proportional to something else. So what's proportional to what? The learning rate for a skill S is of course in math means equal. So this is S equals proportional. So that constant of proportionality that we just talked about is the K. And now what is it proportional to? So it's proportional to the difference. So hopefully you're thinking you're going to subtract something. The difference between the maximum learning for that skill and the amount that has already learned. So I am looking for the difference between the maximum potential for learning and the amount that is already learned. And this is what they are looking for. So we've seen multiple choice questions similar to this, but we do have to be able to read that function and come up with the direct proportionality solution. So when you see the phrase, the rate of change is directly proportional to y. All right, so let's break this down. The rate of change of y. So what are they saying? That is the derivative. Every time I see that word rate, the derivative of y, bam, right there. There's the rate of change of y. The derivative of y is my equal sign. Directly proportional is my k. And what am I proportional to? Y. Okay. So we've got to get that formula down. The rate of change of y, and I'm just common sense, means equal. Directly proportional is my k, and what am I proportional to? Is that y value. So we said, basically, when they give us that formula, you can work it all out, separate the variables and integrate, but you need to know that this turns into y equals CE to the KT. Okay, so when I see that directly proportional, I can write out the formula they give me. Whatever letter they put here is what this one is. So it's y equals CE to the KT. Just to be clear, if they said the rate of change of P is directly proportional to Z. So that would be the rate of change of P, that this time would be dP dt, is equals, directly proportional would be K to Z. When I put that into this form, I'm not going to say y equals this time, I'm going to say p equals because I'm integrating that side. P equals CE to the KZ. So again, it doesn't matter what the variables are, we just have to make sure we're in that same form. All right, so let's apply one quick example here. The rate of change of y, so dy dt, is proportional, is my k, my constant of proportionality, to y. All right, so again, as soon as I write that out, I'm saying, bam, I know this is y equals CE to the KT. All right, so let's plug in what we know. When t is 0, y is 2. So I have 2 equals CE to the k times 0, which is 2 equals C. K times 0 is 0, e to the 0 is 1, so I basically get 2 is equal to C. So now I'm going to plug that in. So I really have y equals 2e to the kt. When t equals 2, y is 4. So now I have 4 equals 2e to the 2k. So let's see, I'm going to divide by 2. So I get 2 equals e to the 2k. To get rid of an e, I'm going to take the ln of both sides. So I'm going to get the ln of 2 is equal to, those are inverses, so they make a 1, 2k. And I'm going to get k equals the ln of 2 over 2. All right, so lastly, I just need to find the value of y when t equals 3. So now I have y equals, I know the c value is 2. I know the k value is the ln of 2 over 2. And what is the value of y when t is 3? Basically, that is the value of y. I got y by itself now. And again, if it's non-calculator, we're just going to be okay with leaving that the way it is. All right, moving on to the next section, verifying solutions to differential equations. Determine whether the function is a solution to this differential equation. So we've seen this in multiple choice sections on some of our practice tests that we've taken so far. So they want to know, if you take f double prime and subtract f, do you get 0? Well, obviously, if you have f, you have to go get f double prime. So first we're going to find f prime. The derivative of sine is cosine. And then f double prime, the derivative of cosine is negative sine. And then I'm literally just going to plug it in this formula. I'm going to take f double prime, so I have negative sine of x, minus my f of x, and say, do I get 0? Negative sine minus sine is not 0. They did not cancel each other out, so I would say this is not a solution. Let's try with the next function. So I need f prime of x, so it's an e, so it's e to the u du. Leave the coefficient, e to the u, times the derivative of the u. So let's see, that's negative 4 e to the negative x. And I need f double prime. So again, leave the coefficient, e to the negative x times negative 1. So f double prime is equal to positive 4 e to the negative x. All right, so now that I found all my terms, I'm just going to see if it's a solution. I have 4 e to the negative x minus 4 e to the negative x equals 0. I would definitely say yes, that is a solution. Something minus itself is 0. And let's try the last one. So f prime of x, remember c is just a constant, so it's a coefficient, it stays. So that's c equals e to the x times 1. So f double prime, that coefficient stays, is equal to e to the x times 1. And if I take that f double prime minus my f, I do get 0. So again, yes, I would say this is also a solution to the differential equation. So I'm just kind of playing their game. I'm finding the pieces that they need and seeing if they are solutions or not. Here's another way they can ask the question. For what value of k, if any, is y equals e to the 2x plus k e to the negative 3x a solution to this differential equation? So again, I'm just looking at the pieces that I might need. I need to figure out what y is, which is given. I'm going to need y double prime, so I'll have to go find that. And then I just want to see if I set them equal, what do I get for k? So let's see. Let's first go get y prime. So if I have e to the 2x, that's e to the u times the du, plus leave the coefficient, e to the u times the du. And I'm going to clean that up, of course, so it looks a little nicer. That's 2e to the 2x minus 3k e to the negative 3x. So I've got y prime, and now I need y double prime because that's what was in the question. So I'm going to go take this derivative. So again, leave the coefficient, e to the u times the du, minus, I'm going to leave the coefficient, 3k, because again, we're assuming k is a constant, it said, we're looking for those values, e to the u times the du. And again, I'm going to clean that up. So let's see, that's 4e to the 2x plus 9k e to the negative 3x. And then I'm just going to carefully substitute that in. So I'm going to do 4 times the y value based off that function. So 4 times the y value, e to the 2x plus k e to the negative 3x, minus the second derivative. So I'm just going to put that in parentheses because I have to distribute that negative. And is that equal to, I'm kind of running out of room here, 10e to the negative 3x. And basically, what am I going to get for k when I solve this? Let's just clean it up. So if I distribute that 4, I get 4e to the 2x plus 4ke to the negative 3x. Again, I'm subtracting, so I have to distribute that negative. Minus 4e to the 2x minus 9ke to the negative 3x. And does that equal 10e to the negative 3x? All right, so a bit of a mouthful. Let's see what like terms we can put together. I think 4e to the 2x and negative 4e to the 2x actually cancel each other out. Then I have these e to the negative 3x's. I have 4k of them minus 9k of them, so I think that's negative 5k. E to the negative 3x equals 10e to the negative 3x. Remember, my goal is to solve for k. I can divide both sides by negative 5e to the negative 3x. Negative 5e to the negative 3x. And look how nice this is. Let's see. The 5's cancel. The e to the negative 3x's cancel. So I get k. Those divide into 1. And 10 divided by negative 5 is a negative 2. So I think we do end up with a solution that k equals negative 2. All right, so living in this differential equation world, we now have differential equations graphically, and those are just called slope fields, a graphical representation of a differential equation. And basically, we'll look at kind of 3 different examples here. So shown to the right is a slope field for the following, for which of the following differential equations. So remember, our goal is literally just to pick a number and see what we get. We want to compare the slope. So these are fairly easy. Sometimes they take a little bit of time. Sorry about that. So let's see. Let's say I pick, here's a fun one, 6, 6. Why did I pick 6, 6? Well, it looks like if I pick 6, 6, I want to see a slope of 0. Okay, so basically there's the point I'm picking and there's the slope. So now I'll just go through. 6 plus 6 does not equal 0. That guy's out. 6 minus 6 equals 0. That's a keeper. Negative 6 plus 6 equals 0. 6 squared is 36 minus 6. That guy's out. So right away I'm at 50-50. And I'm just going to pick another point and think about that. Let's see. I'm going to pick, let's pick something like 1, 1. Well, what's going to happen if I pick 1, 1? I still want a slope of 0. So I get 1 minus 1 is 0. Negative 1 plus 1 is 0. That didn't really help me. So I got to, again, I'm just going to keep picking points. I'm going to go over here, negative 6, negative 6. And again, sometimes you just got to keep picking until it works. So let's see, if I go to choice B, if I go negative 6 minus negative 6, that gets me a 0. And negative 6 is a positive 6 minus 6. Oh, crud, that gets me a 0 still too. All right, so happens to me. We just keep picking. Let's try another one. Let's go 6, negative 6. All right, so at 6, negative 6, I definitely want to see a very negative slope. Okay, it's a steep negative slope. So let's go 6 minus negative 6. Well, that's a positive 12, so hopefully this one's going to work. And if I go negative 6 minus 6, that's a negative 12. So I think that's going to leave me with choice C over choice B. And again, you notice a lot of times points fail, and I just keep going till I get one that works. So this might be something we would see on a free response question. The graph to the right shows a slope field. If the initial condition is 0, 6, so I'm going to go plot that point 0, 6. What is the range for the solution to the curve? So I'm going to then draw in a solution to this curve. Now let's be careful because they threw one little hiccup at us. We are only looking for x values that are greater than 0. So you don't want anybody over here. We're only going to draw the solution in where the x values are greater than 0. So it looks like if I go to the right, these are going down. It looks like I have a 0 slope there, a horizontal asymptote. I'm just going to kind of go to the end. Notice how this one's going to have an arrow on this end, but this one didn't because I did not go past that point. So the question is, how would you describe the range? Well, again, the range are your y values, how low to how high. And I would say it's getting close to 4, but it's not reaching it. And then it definitely goes up to a height of 6, and it does hit it. So I am going to not include the 4, but I am going to include the 6. So again, I'm not actually going to touch 4, so I'm not including it with the open bracket. You could say 4 is less than f of x, but now it's less than or equal to 6 because that's definitely a closed point. All right, now probably the uglier of the differential equations is when they're not in terms of the derivative. How annoying is this? So remember, you have to solve for these in order to start plotting these out. So I'm going to start with these easy ones. I'm not going to start with the x, but I'm going to take the derivative of here. So dy dx equals cos x, dy dx equals negative cosine of x, dy dx equals negative sine of x, dy dx equals sine of x. So I'm going to start with these four, just because this one I would have had to solve for y and inverse cosine, all that jazz. And we'll see if we can narrow it down here. So it looks like when I plug in a 0, that looks like a positive slope right there. All right, so when I plug in 0, I want to get a positive number. Well, the sine of 0 is 0, so that's out. The sine of 0 is 0 times a negative, so that's out. So now I have the cosine of 0, which is 1. So that will leave me with a negative 1. And the cosine of 0 here will leave me with a positive 1. We definitely said it's a positive slope, so that guy's out. So I'm going to go with choice E. So again, I can solve this one for you. Obviously, the derivative of x is 1 minus the derivative of cosine equals the negative sine of y times dy dx. And then I'd have to do 1 over the negative sine of y to equal dy dx, and plug those values in. But again, just make sure you're solving for y in these. So like I said, this is probably the hardest part of the slope fields is when you have to solve for them first, but just remember it's a slope field. You do want to see slopes here. So this is just quick day 1 review of differential equations, and good luck. We'll see you tomorrow.